All right, hi engineering students. This is the second video for week 21. And you can see once again I'm coming to live from my garage, from the workshop where the stuff is all happening. I shouldn't say that everything is happening here because Zach McNeese just delivered a wonderful red oak tabletop to me for Mrs. Jones' desk. Thank you, Zach. It looks amazing. He did some biscuit joinery. You can ask him what that means, biscuit joins. But yeah, this is where we're coming to you from this video. So we are going to actually carry out a little bit of an experiment in this video. This is kind of a version of something we would normally do in class together. I have some equipment here that you can see. This is very much modified, but I think it'll help tie together some things that we have actually been talking about lately with force, stress, strain, all these sorts of things. Let me walk through the setup here. First of all, I have a piece of plywood. This is actually the same gauge plywood that I'm using for both Mrs. Jones and Gil Addison's. If you look at it from the side, it looks like that. It has about 5 ply. It's about 3/4 inch thick. All right, well, yeah, no, it is. I think it's the same one. We have that clamped over here off camera. You can't really see it. Sorry about the focus there. It's way off camera, but it is securely clamped at that end. So this is kind of acting sort of like a cantilever beam sticking out of a wall. If I were going to draw this, actually, it would be like many situations that we have looked at, it would be that kind of arrangement, okay? A fixed condition at the ends, whoops, and then it's coming straight from the wall. And then what we're going to be doing is what we have often done, we're going to be pulling down on it with some kind of force. This thing has a length. So that's all this in practice. I am actually choosing to apply my force for this video, not at the very tip. I'm going to apply it sort of around halfway, roughly halfway compared to back where it's clamped. And let me get to that part now as well. So this arrangement, this is a special device called a force gauge or an S gauge sometimes because of obviously the S shape. The gauge is running back with some wires back over to this device. This is the readout. We've got some very simple controls here, things like on, off. You can choose your different units. It's in newtons right now. You can go to kilograms, pounds, back to newtons. I'm just going to stay in newtons, I think. And let's see. This is going to tell us what this is doing. This can measure both tension and compression forces. So actually, let me just unloop it for a second. Get it out in the open, just catching on the wood a little bit. So here it is in all of its glory. It is a sensor. Look at that very, very descriptive sticker. HF 2000, because it has a 2000 Newton capacity. I can pull on this thing and I can't. Just got to 100 Newtons. A pull. That was harder than I thought it would be. 100 Newtons is about, well, look at this. 100 Newtons, you should know, is about 10 kilograms. Here I go again. There we go. I was a little more ready that time, which is about 22 pounds. Just got there. Back to Newtons. You can also compress, and by the way, you can remove these. These are just attachments, useful for tension with the current setup I have for these eyelets. If you compress it, get the exact same results. But did you notice that when I did the compression, that this is me squeezing right now, there's a negative sign in front. When I pull in tension, that's positive. When I squeeze in compression, it is negative. And that is actually the standard for engineering. I don't think I've said that yet, but the standard sign convention, if you could call it that, is that tension is positive and compression is negative. That doesn't override anything I've told you at all at any point. But in the absence of any other information, that is the the directions that people typically choose. There's some sandpaper. Don't need that. Don't need that. Sorry, my desk is a little full of stuff. All right, there we go, back to it. That's just my standard black cord. All right, what else? Well, actually, let me just quickly tell you. So what this strain gauge does, this strain gauge, if you took off these two screws and had a look in here, this plate comes away. You've actually got some electrical resistors there. Okay, this is sending a, like a current. You have an electrical resistor, and as you pull on this, even though you can't really tell, this thing is actually changing shape. Remember, I've told you that everything that is rigid changes shape when it gets deformed. Okay, it always stretches or squeezes. Even if you can't see it, it is doing that. And as this thing changes its shape for squeezing or stretching, the resistance of that little resistor in there changes. The electrical properties change, and that's what this is picking up on, and that is calibrated to match to tell you what load. It's kind of a handy little piece of equipment. So here's how we are going to do this. I'm just going to simply pull on this thing with my hand. You can see even with gentle little pulling motion, we get measurable results. I'm going to measure this line, okay? So let's actually start us off here and try and do this according to the camera. So this right here, this would be 0 newtons. And you know what? I'm thinking it might be better to do this in Sharpie. All right, hits it right there. Once again, that is 0 newtons. And yeah, this could be clearer too. There we go. And as I pull, that is going to move. And the point of what this experiment is supposed to show is that the deflection action is linear. Okay, this is going to be a little eyewitness example of Hooke's law, which says that when you apply forces, you get deformation, not deformation, deformation, and it is linear. This is like a y equals mx plus b equation, but there's no plus b because when there is 0 load, as you can see right now, it's still in its original position. I apologize for the camera autofocus. That's a little bit annoying. I don't think I can fix that. All right, so let's see how we do here. We're going to try to mark these things off. If you don't understand where this is going, hopefully you'll see it as it does. So I'm just going to start to pull down. I'm going to do it. Remember, this is securely clamped. I'm going to try to wait until I just pick up on, there we go. So that is right about where we get 20 newtons worth right there. Okay, see that 20, 0. Now, if you're wondering why it was just nothing, 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 and then suddenly bang 20, it's just the way that sensors work. They don't want to kick in the sensor until you sort of reach like a threshold of things actually happening. This kind of sensor is not reliable. It's not scaled for small forces. 20 newtons is still a relatively small force. That's about 2 kilograms, about 4.5 pounds. Yeah, that's why it kicks in that point. What we will see is as we keep pulling on this, and hopefully our whole rig stays as is, you see now we get like individual newtons. So I might go until I get to 30. Let me write that one in. It's actually kind of hard to write as you're looking at the camera, not at your actual hand. All right, there was 30. Let's keep going. By the way, when you do tests like this, you always want to do things slowly. It's one of the basic rules. Okay, I'm having to pull with some force now, but there's our 40. I'm gonna just make a bit of room. Am I right in there? Okay, there was 40. Now, notice I'm letting go each time because I want to show you something. This piece of wood is rebounding back to its original position after each load cycle. That's what we call that. Okay, we load it, we unload it, and it keeps on going back. Now, what this tells me is that this piece of wood right here is functioning according to Hooke's law right now. F equals kx, or you recall, we're not really going to use it for this video, but we said stress equals Young's modulus times strain. That is also Hooke's law. That's just the intensive version. This is the extensive version. But the idea is that it is functioning like a nice linear spring, and it's coming back each time. That just tells me that none of these fibers are getting like damaged or torn or broken or anything. My rig that's got it clamped at the other end that you can't see, it's all holding. This is a good experiment so far. Let's see if we can get to 50. See if we can get to 50 without. I'm more worried that my clamp is going to give way because I'm generating a lot of moment right now. Okay, back up to 40. Great. Let's keep going. There's 50. And we'll release. I'm just going to do it over here because I'm kind of clumping up with my words. Okay, there's the 50. Again, we went all the way back. Yeah, it went back, yeah. All right, let's try again. Nice and slowly. 20, 30. There's the 40. 50. If this gives way, it's going to give way all at once. And I hope it doesn't knock my camera over because my camera is part of my computer. All right, and back again. I feel like a calm Pilates instructor or something. Just breathe in and out again. Oh, this is good. Okay, there's something else that I'm going to remind you of too that we've always said when it comes to Hooke's law, and that is that it is really only valid for small deflections or small deformations. These are not small deformations, okay? So I'm kind of bending the rules of what a proper Hooke's law experiment is. I'm aware of that, but it still is actually proving the point quite nicely. I don't know if you can see what I mean when I say that it is proving my point quite nicely. Should we try to get to 70? I'm all for it. Here we go. The other danger here is that my piece... Come on. Ooh, I heard something crack. I don't think it was me. Okay. And back again. Is it going back? It's kind of going back. I need a little bit of persuasion. I have a feeling like that's where I should leave it. I think I heard something just shift a little slightly. And also our deformations are getting so large that it really will start to invalidate the experiment. Okay, so let's talk about what we're looking at here. At 0 newtons, we had actually, let's see. All right, I'm gonna have to start to measure stuff now. What am I gonna do? I'm gonna unclamp, get my wood out of the way. Give me 1 second. Okay, come on. That's it. All right, just want to get out of the way. Still want you to see it, but I'll just move that a little bit too. We'll get those lines out of there. All right. So we have the places where the force measurements were taken. Now, if we say that this is, let's say this is 0, and man, I'm really regretting what I'm about to do here. I'm hating this 100%. I'm going to measure in inches right now. Mixing newtons and inches has got to be, this could be the biggest failure of my engineering teaching career, but we're going to do it anyway, because I have an inch ruler here. I'm looking around. I don't see anything metric in my workshop. I'm embarrassed to even say those words. Don't tell anyone in Australia that I said that. Okay. You know what? We've got a little bit of glare. I'm going to switch to a tape measure. There we go. That's much more visible. And let's see. Imagine that I was kind of clipping this tape measure onto that. What are our measurements there? Well, you know, maybe it's best just sort of talking in round terms. I hope what you can see, sorry, this just may not lend itself to the exercise, but I hope that you can see that this distance, let's say from 0 to 20, okay, 20 newtons worth. You know, I'm just going to measure it myself. Hold on. You might not see because of the glare, but all right. Okay, it's roughly half an inch. Roughly half an inch. Okay, getting down to there. So from 0 to 20 newtons is about half an inch. And I hope that what you can see is, like, if you go another 20 newtons, let's say 20 to 40, that distance, forget 30 for a second, 0 to 20 is basically the same distance as 20 to 40. Like, it's close. This is me with a Sharpie on a piece of paper pulling on a little stick of wood. This is really close. Yeah, it's actually pretty good. I'm gonna mark it off. I'm gonna say this is 1 inch. Yeah, that's not too bad. Yeah, this one, the 30 Newton mark, that's all right. I reckon I can put it in there. I can squeeze it in. That's 3/4 of an inch, and we can sort of keep that going. You know, this here is 1.5 inches. This is about 1 3/4 inches. It's a little too tight to write in there. Sorry, that's 1 1/4 inches. Okay, not feet, inches. There we go. Okay, sorry if that's not very legible, but I think you can see it. This is actually quite remarkable. Like, this is acting in a very linear fashion. As I double the force, I'm doubling the displacement. As I double the force, it's proportional to the displacement. I could even start to plot this kind of thing here. Haven't shown you any graphs of this yet, so this is actually quite an important moment. No engineering pun intended. All right, let's do a little graph. Sorry, it's a little bit rising up there. When we show these graphs, we always show the deformation, the motion on the bottom axis. We are measuring right now in inches. As I said, I'm hating everything about that. That's what I happen to have in front of me. And then on the vertical axis, we're showing forces, and we're measuring that in newtons. I guess I just should have put it into pounds. You know, it is what it is. We always show the load on the vertical axis and the change of shape, the deformation, the elongation, the stretch, the compression on the bottom axis. When I had 0 newtons and 0 inches, that would be this data point right here. Okay? 0, 0. I got to, well, I could sort of mark it off here. Let's see, we've got 10, 20, 30, 40, 50, 60, 70. I'm just doing that obviously by sight, not through measurement, but the point will be well taken. And then over here we got like let's say half an inch, 1 inch, 1.5, 2. Let's do it like that. 1.5, 2. Okay. All right, so my second data point, at 20 newtons, I had ½ inch of stretch. That would be this right here. At 30 newtons, I had 3/4 of stretch, which is this right here. At 40 newtons, I had 1 inch of stretch, right there. At 50 newtons, I had 1 1/4, kind of somewhere there. At 60 newtons, I had 1 1/2. And at 70 newtons, across there, I had 1 3/4. Okay, something like that. I can then draw a line of best fit. Now, as it happens, this was so close that I just kind of, obviously fudged the numbers a little bit because I knew where it was going, and I definitely rounded off as I wrote those down with the rule, but it was very, very close, as you saw. But if you get your data points and they're not perfect, you just draw a line of best fit. Okay, a linear line. Okay, there's a redundancy for you. Draw a linear line best fit. That line is going to go through 0, 0 because this y equals mx plus b equation doesn't have a plus b. So you know that it's going through the origin. In this case, what is the rise of a run? What is the slope? The slope is, I can almost pick anything. Let's say I'll pick this first data point. Rise of 20, run of ½ Slope is rise over run. So we have a rise of 20 newtons over a run of ½ an inch. Oh, I'm just hating what I'm doing. 20 divided by ½ is 40. So the slope here is 40 newtons per inch. And what this really is, this is the K value, okay? This is the K in the F equals Kx equation. 40 newtons per inch. Now, what is that saying? That's saying that for this very, very particular experiment, I'm not saying like all plywood, all lengths of plywood, all sizes, all shapes of plywood. This is not a general statement about plywood or these kind of bending experiments. All this is saying is right here, when this video was recorded under these conditions with this piece of plywood, which was this length, this thickness, this width, and moreover, the strain gauge was attached at this location, like all of these specific conditions that you could possibly think of, that's the amount of force it takes to move the needle by 1 inch. Okay, 40 newtons per inch for this experiment right here. This is about as like extensive of an idea as you can possibly get. It only applies to this thing. If this thing were twice as thick, the result would change. If I move the strain gauge to be a little further down or a little further up, that would have resulted in a different force measurement. So this would change again. Anything you change would change this result. So this is an F equals Kx situation. Pardon me. But it's very valuable. I can see, all right, if I apply 40 newtons, I get a motion of 1 inch. If I were to apply 80 newtons, I could kind of predict I should get 2 inches of deflection. Now, as I've been saying, the further and further we go along, as the deformation gets greater and greater, Hooke's law gets less and less valid. It's just not designed for big deflection things. But for the little small kind that we just do, which is how steel and aluminium and metals behave in particular, carbon fibers and things like that, it's very, very useful. Wood is relatively not stiff, so it changes shape quite a lot. But that is actually a beautiful set of results, and I'm very happy with it. Now, you might be wondering why I didn't run an experiment that's dealing specifically with stress equals Young's modulus times strain, because that is what we have just been doing in our most recent videos. This stuff was actually like springs back in first semester. We've mentioned it for sure, but we've been trying to put our focus here. So let's think about that. How could I take these results and talk about this kind of stuff? What stress am I measuring? And the answer is, it's actually kind of hard to say what stress I'm measuring, because stress is force over area. Very important idea here. This is crucial. But what area am I talking about here? You know, for simple tension compression situations, like let's say here's a little block of wood and let's say I'm put up to my fist and I'm compressing it, I'm squeezing it with all my might. That's a clear compression situation. And it's also pretty clear what the area under consideration is. I get my little carpenter's square and I see, oh, it's like 1 3/8. You see that? 1 3/8. Those markings are eighths, 1, 2, 3 of them. Measure the other way. Oh, it's also, it's maybe a little itty bitty bit, what am I saying? A little itty bit smaller than 1 3/8, but it's pretty close. So this area of this piece would be 1 3/8 inches times 1 3/8 inches. And this is why I love metric so much, because what in the world is happening? 11/8 times 11/8 equals 121/64. How is that going to help anybody? Look, it's, what can we say? That's about 2, yeah, roughly 2 square inches, very, very roughly, because 60 times 2 is 120, very roughly. So we would say, okay, let's calculate the stress. We could get our little strain gauge here. We could actually unattach this. Turn this thing back on, it timed out. See that 2000 is showing there, 2000 Newton capacity. Okay, that's it in its stripped down version. Okay, we can get that. Interlace our fingers for extra strength. Oh, look how many newtons I'm developing there. So we could do an experiment like that. We could say, all right, in fact, look, if you want to get all fancy, you could even get a clamp. You could say, okay. What if we did this kind of thing? Tighten that clamp up. And as we do that, I might just center that a little bit more so it doesn't pop out by accident. Very important to center your load if you can for these kind of experiments, or you can get weird things happen. Look at this, as I clamp this down, easily get into the 300s, which if we change units, that's about 37 kilograms, about 81 pounds. This is about the force which apparently Mrs. Jones' desk can handle with the 2-inch caster wheels. And like I say, that's kind of easy to decide that that's the stress. We have a force there of 355, whatever it is. We would divide that by the cross-sectional area, because for a compression test, that's what you're talking about. It's the cross-sectional area. I'm just going to release. And you'll have a stress. Okay, and I'm not going to calculate a stress in newtons per square inches. That really will drive me over the edge, mixing those units like that. But you understand my point. That's an easy thing to understand. But when you are doing, back to what I was saying, when you're doing this bending thing where you're like pulling down on something, what's the area? Is it like the cross-sectional area there that you're pulling at? Well, maybe. Is it the area of like the bottom edge or the top edge or something? It's not really so clear cut. It's actually way more complex than that. So it's very hard to turn these forces that we had here. It's pretty hard to turn those into stresses because of the area problem. Where's the area? The strain is also a little bit hard to calculate because strain, remember, is defined as what's the increase in length divided by the original length. Are we talking, when we talk L, are we talking like the length of the whole thing back to where it's clamped at the wall? Is that what L is? And then is delta L, is that this deflection that we're measuring as it goes down? But how is that length related to that overall length? Is that what should feed in here? Yeah, probably not. Again, if you're doing a compression test with real sensitive equipment, you know that you're talking about the shortening is the delta L. And then the L is the original length. Okay, so it's very clear cut what the strain is referring to. Not so much for this bending test. So this doesn't translate well into this for this particular type of test. It works really well with compression tests, with tension tests as I pull on it, but not so much for bending. However, with this kind of basic lab equipment I have, the bending test is way easier to run. And it still functions according to Hooke's law, wherein proportional load increases give proportional deflection increases. So that point is illustrated, but don't expect that you can get a Young's modulus out of this. It's pretty hard to do unless you really, really get into it. Fortunately, we can look up tables because lots of people around the world have done lots of experiments with plywood and they can tell you what Young's modulus is because they've gotten plywood, they've squeezed it and stretched it and watched what happens and measured it very precisely. They may have measured it with a device like this. Here's my last little bit of show and tell for this video. This is a strain gauge. Too much talking. This is an inch strain gauge. Oh, wait a minute. I think that's what should be happening. That's a movable face. With this little handy strain gauge here, you rotate the face until the 0 is there. And then as your piece moves, this is an extremely sensitive thing. This is measuring in very small units of 0.001 inches, as you can see there. And it goes all the way around until it reaches the actual, almost practically 1 inch. See, this is the scale of measurement here from 0 to 1 inches. That's the increments that we're looking at around the face, 0.001 inches. Okay, so in other words, thousandths of an inch. And then you see that little center dial in the middle as well is also going around and marking off the hundreds as that happens. Okay, you have 100 increments around there, then you got 10 there. So 10 times the 100 gives you the full 1,000 that are contained within 1 inch. It's all right there. So yeah, this is the type of experiment you could do, where you would place a strain gauge like that right there. Once it's in position, you would, where did it go? You would just level it off, and then as you pull down, that thing looks like a crashing aircraft spinning around and around with an altimeter. That's what it makes me think of. Okay, and it reacts to the load. So that's a much, much more precise way to get the measurements. I just didn't bother to set up a whole rig like that because it would have been a little more time and fuss and bother than the results warrant anyway. Okay, so that gives you a little taste of how stress and strain and, well, not really stress and strain, but force and deflection at least get measured in some practical experiments. If you want to study material science at university, then they will have big tens of thousands of dollar machines where you get a little sample piece like this, you put it in a machine, it clamps it at both ends, and it pulls on it with like a perspex cover until it actually does break and you get the results and they feed straight to a computer and you get something like my little graph here, except it's computer generated and it looks great, and you run the line of best fit in Excel and it's all there. But the principle holds. So thank you for watching. A little bit of a shorter video this week. Next week is the last one of our statics in action series, and then we are going on to coding and robotics, and that is going to be a whole lot of fun. So thanks for watching. As if you had a choice, leave some comments on the discussion board, and we'll see you guys around at school.